Hello all. In last class, we saw different application of Gauss law. That is, Gauss law is applied to the spherical shell. The Gauss law is applied to coaxial cable. Gauss law can be applied to point charges. Gauss law can be applied to line charge, and Gauss law can be applied to sheet charge to find electric field density and electric flux density and electric field intensity. In this class, we will see first revise what is divergence. That is, we saw in first chapter. So just we will revise that, and then we will, using that divergence concept, we will arrive expression for Maxwell's first equation and the divergence. We will see what is divergence theorem. So as we know, divergence at point due to a vector field is a ability to diverge from that of point. So that is measured in terms of called divergence. If I consider point P, if you see here, you have three diagrams. So A, B, C. In diagram A, you can see the at point P, all the fields are moving out from point P. So I can say the divergence of at that point of vector field is positive. Similarly, the here at point P, the field is enter into point P. So I can say the divergence at point P is negative at diagram B. Similarly, same amount of field is entering to point P and leaving from point P. So I can say at diagram C, I can say the divergence at that point is 0. So mathematically I can express divergence in terms of surface integral per unit volume. So I can say divergence of A can be represented as limit delta V tends to 0. It means the unit volume tends to 0. The volume shrinks to 0. So divergence of A can be written as limit delta V tends to 0 surface integral of A dot ds divided by delta V. Delta V is unit volume. So I can represent the delta divergence of A is equal to dou Ax by dou x plus dou Ay by dou y plus dou Az by dou z. So this is a one more representation for divergence of A. We know that dou A by dou x, dou by dou x plus dou by dou y plus dou by dou z as is a operator called del operator. So I can write using del operator, I can write divergence of A can be written as del dot A. So del dot A is also divergence of A. Now we also saw what are the different formulas for different coordinate system, the divergence in different coordinate system. So in Cartesian coordinate system, del dot A can be written as del by del x into ax plus del by del y into ay plus del by del z into az. Similarly in cylindrical, it is 1 by rho or 1 by r into del by del r a r cap plus 1 by r into del by del phi into a phi plus del by del z into az. Similarly, this is the formula for spherical coordinate system. Using the concept of divergence theorem, we will arrive expression for Gauss law in point form or Maxwell's first equation. So Maxwell's first equation we will derive using the concept of divergence theorem. If you consider the D as a vector, D means the electric flux density as a vector, the divergence of electric flux density can be written as del dot D, which is equal to, that is divergence of D, which is equal to limit, as per definition of the divergence, limit delta V tends to 0 surface integral of D dot ds divided by delta V. I will take this as equation 1. Now we also know that divergence of A can be written as in terms of different the components with respect to x, y, z, that is the ax, ay, az. So del dot A can be written as del ax by del x plus del ay by del y plus del az by del z. So similarly I can apply same concept for divergence of D also. So this equation divergence of D can be written as divergence of D is equal to del by del x into dx plus del by del y into dy plus del by del z into dz. Now according to Gauss law, I know that the q, that is psi or q, which is equal to surface integral of d dot ds. The q is equal to surface integral of d dot ds. Now I want to find what is a charge per unit volume. I have to find charge per unit volume. To find that, I will divide both the sides by delta V, that is, I will divide both the right side and left side by delta V for this equation. So after dividing, I will get Q by delta V, which is equal to d dot surface integral of d dot ds divided by delta V. Now I will apply to find the when volume shrinks to 0, what is the charge per unit volume. To find that, I will apply both the sides a limit which is delta V tends to 0. A limit with delta V tends to 0. I will apply that limit for both the sides. Then equation will become limit delta V tends to 0 Q by delta V, which is equal to limit delta V tends to 0 surface integral of d dot ds divided by delta V. But we know that in chapter 1, that is in the electrostatics, the Coulomb's law, we saw that the charge divided by unit volume gives me the charge density. The charge by unit volume gives me the charge density, means it will give me volume charge density. So this limit delta V tends to 0 divided by Q by delta V can be written as rho V, right? So limit delta V tends to 0, Q by delta V can be written as rho V. So substituting this in previous equation, we will get rho V is equal to limit delta V tends to 0 surface integral of d dot ds divided by delta V. So I will take, now comparing this with first equation, I can write del dot d is equal to rho V. I can write del dot d which is equal to rho V. So or divergence of d which is equal to rho V. The del dot d which is equal to volume charge density. So this equation is called as Maxwell's first equation. So that is del dot d is equal to rho V is called as Maxwell's first equation. And other names for this equation is the Gauss law in point form and Gauss law in differential form. Both the names holds good for this equation, Gauss law in differential form or Gauss law in point form. So these are the different names for this equation or Maxwell's first equation. The Gauss law in point form is stated as the divergence of electric flux density is equal to the volume charge density at that same point. The divergence of electric flux density in a particular medium is equal to the volume charge density at that particular point is called as Gauss law in point form. So using this, we will solve problems later. So before going to problems on this, we will see what is divergence theorem next. So divergence theorem is mainly used to convert the surface integral into volume integral. If you have surface integral, so to convert into three-dimensional integral, we will use divergence theorem. So you know, according to Gauss law, you know that Q is equal to surface integral of d dot ds. So this is, I will take this as equation 1. So if I take a volume, then to find charge enclosed in that volume, so I can write, if you know the charge density of that, the volume charge density of that volume, then I can find the charge at that particular volume can be written as Q is equal to volume integral of rho V into dV. Now, so according to Maxwell's first equation, we know that rho V can be written as in the terms of divergence. The volume charge density can be written as in terms of divergence. So I can write del dot D is equal to rho V according to Maxwell's first equation. So substituting this equation 3 in equation 2, I will write Q is equal to volume integral of del dot D into dV. Now equate this equation 4 with the equation 1, then I will get, so surface integral of d dot ds is equal to volume integral of del dot D into dV. So this equation is called as divergence theorem. This equation is called as divergence theorem. The main use of divergence theorem is used to convert the surface integral into volume integral. We can state divergence theorem as the integral of the normal component of vector field over a closed surface is equal to volume integral of this vector field. So volume integral of same vector field over that same surface. Okay. So the statement of divergence theorem will be the integral of normal component of any vector field over a closed surface is equal to the integral of divergence of this vector field throughout the volume enclosed by that surface. That means the surface integral of any vector field is equal to the volume of same surface. The volume integral of divergence of that vector field will be equal to surface integral of the same vector field, okay, over a surface integration, and the surface integration can be converted into volume integration using divergence theorem. So using this divergence theorem, Maxwell's equations, and the application of the Gauss law, problems on this we will see in the next videos. And so after solving the problems, we will go to module 2, and I'll upload the videos in the next coming days on module 2. Thank you.